So my name is David, and I'm working at Elastic for 3 years now. So don't trust me. Try everything by yourself, and because I'm a bit biased now. Actually, this talk is based on my own experience when I was working for the French Customs. I put in place the NoSQL world at the French Customs Services and Elasticsearch, and this is what I'm going to relate today. But I'm going to use another use case than the French Customs. And the talk will be about how you can add advanced search on your existing application. So the use case we are going to use today is about marketing data. Let's say that we are collecting some data about persons, physical persons, such as the name, the address, the birth date, some marketing counters, how many times my user click on my cars button in my mobile application, for example. So marketing counters. And today we have existing running application. I choose here to use something like, we code in Java. So I'm using here a Tomcat container, and my application is running here. I'm speaking with a MySQL database here, and I have a front end built in AngularJS. So it's not that old application. I don't want to focus today on GSP pages. This is not the purpose of the talk. I'm going to talk about the backend. So this is the reason I have a modern front end here. We have this application, and we want to move the search part using a real search engine. So what do we have? We have our domain layer, and we have Java beans. We have the the top level bean is a person, which contains the name, the date of birth, the gender, also the address, which is another bean here, containing, for example, the country, the city, the geolocation point here, which is a latitude and longitude, and also the marketing counters, as I said. And we have the similar things in the database, so a table for person, table for address, and table for marketing data. This is what we have. So let's have a look at what is running now. I will show you this QR code again at the end of the session, so you will be able to copy basically the GitHub repository, and if you want to replay that from home. So let's look at what we have. So I'm running already my application in my, I hope the sound is correct, in my IntelliJ ID. So it's already running. If I look at what I have for now, I have nothing in the database. I have a simple interface where I am able to search. The first thing I need to do is to inject some data. So using this API, I'm going to inject randomly 10,000 people. If I look at the search part now, so data are streamed to the MySQL database. And if I start to search, I can see the data coming. If I search for people named Joe, I have some people named Joe, some people living in France. Okay, so it's working basically. And I have also the advanced search feature, where I'm able to search in the name field, in the country field, and in the city field explicitly. So let's say I want to search for Joe, living in France, in my city, here, searching. Okay. So this is what we have. If we look at the code behind the scene, let's move that. So I have a first method, which is here a find like Google method. So this is for this simple search here. So my injection is over. If I look, how long does it take? So I was able to inject around 300 documents per second here. Okay. So looking at the code back, so the find like Google method is getting from the interface the query. And we are using Hibernate here. I'm going to generate a query using Hibernate. So if I look at this code, what I'm doing here, I'm doing a search. So using this form, and I'm creating a join with the address table here. So I'm searching for what the user set inside the name field, inside the address.country field, and address.city field. Okay. So that's basically it. If we look at the advanced search, so I'm getting from the interface three information, the name, the country, and the city. So this is really similar. I'm building, again with Hibernate, search. So on the name field, I'm searching explicitly for the name, address.country, and address.city. So this is exactly the same thing. Okay, let's move back to the slides. Should be the slides. Where are my slides? That's funny. Okay. So we want to connect now our existing application to Elasticsearch. And what can we do for that? So we can use an ETL. So an ETL is basically a tool which is able to extract data from a source, then transform this data to either JSON document, and then push this data back to Elasticsearch cluster. So ETL tools are, for example, Mule ESB or Talent. Those are great tools for that. But we have an issue here. Actually, we are trying to poll the database every 5 minutes, for example, and we are trying to find what is new in the database or what has been updated in the database. So polling the database every 5 minutes is not real time, right? If a user creates a new data in the database, then you have to wait for 5 minutes before you are able to search for it, actually. So it's bad. What happens if you delete something in the database? When you are going to run the SQL again against the database, you need to be aware that something which is not coming back has to be deleted in Elasticsearch. So that's super tricky to solve. Maybe you can use a trigger, but okay. Or you can use maybe technical table saying, oh, I have deleted something. So, but you have to do a lot of things. Actually, also, if you have a complex model with a lot of collection of properties, collection of properties, then the SQL you have to run will be super hard because it's hard to produce a JSON document within only one call. So I prefer to use a direct connection for that. And actually, why you should read the database again if you have already your data in memory. So let's imagine that I have my bin here in my memory. Within the same transaction, I am putting my data into the database. I can use the same bin, serialize it to JSON, and then send it to Elasticsearch within the same transaction. Right. This is something we are going to do. Actually, when you delete a document, this is the same story. Because within the same transaction, you can simply say to Elasticsearch, oh, delete the same document. Right. This is something we are going to do. But first, I want to talk about the document design. ND for that. So I'm going to use a private final object mapper class, which is coming from Jackson. Okay, and as my RestX project already provides that, I can simply inject that here. Okay, this dot mapper equal mapper. Okay, now serious things. I need to save my document. So I'm going to use my client, and I'm going to say, okay, I want to index something. I'm going to prepare a new index request. I want to save my document in an index called person here. The type of the document will be a person. And the ID for this document will be the reference I have within my bin. And I need to provide the JSON document. I forgot about it, so I need to build the JSON. So using my mapper, I can say write as bytes or strings. We support both, so let's say bytes. So I'm going to serialize my bin as a JSON document here. Let's send that here. Okay. This is generating an array of bytes. And I need to provide that to the index request. So what is the source, the JSON document? So this array of bytes. And then I need to execute that and get the response back. And, okay, missing that. Okay, so I have the save method now. So basically in 2 lines of code, you are able to send something into Elasticsearch. So that's not the hard part. I mentioned something, I have an exception here, of course. So imagine that Elasticsearch is raising an exception when you are saving the data to Elasticsearch. What you can do? You can roll back the transaction and say, oh no, I don't want to persist my document into the database. This is not what I choose when I was working for the French custom, because to me saving the data into the database is the most important thing. So if I have an issue here, I just want to surround with try catch and log that to my ops. Okay, error. Houston, we have a problem. Yeah, with the exception. You can do what you want here. Okay, let's do the same thing for delete. For example, here I was deleting a person from the database, and I want to show you that it's super easy to delete something into Elasticsearch. So let's use the same DAO. I want to implement a new method named delete, and I want to remove a person by its reference here. Okay, so we implement that. What I have to do, use my client, do a delete with a new delete request. What I want to delete is existing in index name person. The type is person, and the ID is the reference. And I just need to call it and get the response back. Same is happening here. I can throw some exceptions. Let's do this. Okay. So I will have the same issue here. I need to basically try catch again and log whatever I want. Okay, so let's see if this is working. The first thing I need to do, obviously, is to start Elasticsearch. So I have here an empty Elasticsearch node. So I need to start it. And I'm going also to use a Kibana. So Kibana is an application we built, and I'm going to use a feature within Kibana, which name is the console. So I'm going to be able to send some REST requests to Elasticsearch. So bin/Kibana. Okay. So my node is running. So 2 ports. The REST port is this one, and the Java transport port is this one. And Kibana is started, so I can open this now. Oops, there we go. So if I look at my console and I say, give me the existing indices. Okay, for now I have only internal index for Kibana. I have nothing else, right? So let's restart the application here. Okay. Should not take a long time. Creating. Okay, so it started again. So let's inject now our 10,000 documents again. If I do that, now I can see that my data is still coming from the database here. So the data is in the database. And if I look at the same call we have seen before, so now I have index name person, and I can run some search within this. So let's run the search method. So I have indexed so far that number of documents, and here are the 10 first documents. So we can see that those documents have been serialized into JSON, and they are streamed to Elasticsearch here. But still, our application is still using the database to search. So we need to modify now the search layer. Let's do that. So in my person service and the search method, where is it? Here. So I'm going to remove all that code, and I'm going to replace that to some Elasticsearch call. So first, I need to create a query, Elasticsearch query. So, oops, what did I say? Which one is it? This one? Yes. Query. I need to make some decision. Let's say that the user didn't enter anything. So strings as text here Q. So if it's not the case, if I don't have any text, I want to build a first query. Yeah, my French accent, you know. Which is a match all query. Which means give me anything. This is exactly the same thing I run in the REST console already. So give me anything. Or if I have something in queue field, then I want to run another query builders again, which is a simple query string query. I'm searching for queue, and I'm searching this into several fields. For example, I want to search in the name field. I want to search in the address.country field, maybe address.city field. I can search in another field if I want, because Elasticsearch is indexing basically everything. Okay, so I have my query now. I'm going to send this query to my Elasticsearch DAO, and I'm going to create a new method search. I will pass my query. I will also pass, just to show you how pagination works, the from and size parameter if you want to do pagination on your application. That's super easy. So let's implement that. So I have this. What I need to do here, I need to say, with my client, I want to prepare a search operation. I'm going to search within the index name person. The type I will search in is, I will search only for document type person. I don't have to give that, but this is just to show you how it works. I'm going to set the query. Oops. Query. With the query I just received from the method. Let's implement the from parameter, so it's super easy. You basically have to set from and size. So this is the size of the page and from which document you are starting. And then I'm executing that and get the result back. And I can, so this is my response, and I can return that response Okay. So now I have a response here. What I need to do here is I just need to send that as a JSON document to my front end. So I'm going to do response to string, and that's it. Okay, let's have a look at the advanced search part. So same thing, I'm going to remove all that stuff. And I'm going to code very fast. Yeah, very fast. Okay, so what it does here, it looks like for the name field, country field, and city field, we are getting from the interface. And if I have nothing in name and country and city, then I'm running the match all query, as we have seen before. Otherwise, we need to construct a Boolean query. And if I have anything in name, then my field name should match, what the user gave me as a name field should match what I have in name field. So we are adding a must clause to our Boolean query, so it must match. This is the same thing here for address.country and address.city. So it must match all the criteria if you have any criteria here. So this is my query, and I'm using the same Elasticsearch DAO I have built before, and running this query, and then sending the result back to Elasticsearch. So let's restart the application, and see now the query and the search part running into Elasticsearch. Okay, started. So now, if I search within Elasticsearch, I'm searching within Elasticsearch here. If I search for Joe, oh, it doesn't work. But only the full name is working. So this is something we need to fix, right? We have a different behavior with what we have seen before. But I can search for the gender field, for example. Let's look at the advanced search. So here I have Joe is not working, but if I put the full term, it's working. Same for Italy and Turin. Okay, so it's working. It starts to work. Not ideally yet, but it starts to work. Before fixing that, I want to show you a more efficient manner to index data into Elasticsearch. And instead of indexing one document by one document, it's better to send to Elasticsearch like a batch of index requests and delete requests. So this is what we call the bulk. And we have a class for that. The name is the bulk processor. So I'm going to build that here. So this specific class, I need to create this class, okay. And I need a logger also. Demo logger. Okay. So what it does, it creates a bulk processor. I'm going to add actions within this bulk processor, and every 10,000 actions, I will flush the bulk to Elasticsearch. Or every 5 seconds, even if I don't have 10,000 actions within my bulk, I will flush that to Elasticsearch, right? And I have a listener, so I can do whatever I want before the bulk, after the bulk, and after the bulk if I have an exception. Okay. What I have to change here, it's super easy. I need to say, okay, instead of indexing into Elasticsearch, I want to use my bulk and add my request. So I don't need to execute that. The bulk processor will execute that for me. And the same is happening for delete. Bulk processor dot, I'm adding the delete request. That will be really much more efficient than indexing one document per one document. Okay. Let's try to fix the issue we have with the search, the partial search here. This is due to what we call the mapping into Elasticsearch. So Elasticsearch comes with a default mapping when you index your first document and you don't say anything to Elasticsearch. So this is the schema we are using behind the scene. And we are generating that and we are guessing that from what you send, from the JSON document. But sometimes Elasticsearch is not doing the right thing. So you have to adapt your mapping and, for example, give some text analyzers you want to apply to the strings in order to be able to search as you want to search. So here I want to do like an autocomplete search. If I search for the first characters, I want to be able to find the content and not only the full terms. So I need to adapt this mapping and modify that. To do that, I created an open source project. Sorry. The name is Elasticsearch Beyonder. So it's open source. You can use that. And basically what it does, it's going to look within your class path. And if you have, oh, it's already there. I should have removed that. Okay. If you have a directory existing within your class path, where is that directory? The name by convention is Elasticsearch. If you have within this directory another one, which is the index name, then Beyonder will take care into account what it's inside this directory. So if you have here a JSON document, name person.json, so this is the type.json, then you can provide here your own mapping if you wish. So this is what I'm doing here. I'm providing the mapping to Elasticsearch. What I'm doing here, I'm saying, okay, for my address.city field, this is the same thing as we have seen before. It's still a text field, but every time you index content which is coming from address.city field, I want you to copy this content to another field. The name is full text. And I have defined this other field, sorry, which will be generated at index time with those analyzers. So I don't have enough time to speak into details what is the analyzer, but basically this is what is going to solve my issue. So here I'm defining at index time the Engram analyzer, and at search time another analyzer name is simple here. And I'm also saying that for this city field, at index time I want to generate automatically some subfields. So if I search into address.city.autocomplete, then I will use the same Engram strategy I just mentioned. And also, if I compute using address.city.ags, then I won't touch the text. I will index the text as is. So this is what it's doing. And I'm doing that for city field, for country field, so which is copied to full text as well. What else? For the gender and the name field. Okay, this is what I'm doing here. I need to provide the definition of my Engram analyzer. So to do that, I'm going to provide index settings. So again, Elasticsearch Beyonder will use this underscore settings.json document automatically. And if you have that, when you create the index into Elasticsearch, then it will apply what you have. So you can define the number of shards, number of replicas, but here I'm just going to define what analyzer I want to use. So I'm going to use my Engram analyzer, which is going to use the Engram tokenizer. And for those who knows, I'm going to use the edge Engram, which is basically going to index not only the full term, but every single, from the beginning, every single digit. So if, for example, if I want to index Joe, I will index G, G-O, G-O-E. That's what I'm going to index into Elasticsearch using this Engram. Okay. I need to call my Beyonder class because I didn't call it already. Where is my here? Okay. So in my constructor here, I'm going to use my Beyonder class, and I'm going to start it on a client. Okay. Just run with try catch here, that's fine. I need to remove the index into Elasticsearch because Beyonder is not going to replace your data if you have already data. Sorry, so I need to do a delete call on the index name person. So I have removed all my data here. And let's restart this. I'm going to restart this in debug mode now because I will be able to now automatically reload the classes and do some hot reload things. So if we look at the logs, yeah, we can see that Beyonder has started, rock and roll. It recalls me the previous session. And let's index again our 10,000 documents. Okay. So Beyonder should have created the mapping I'm expecting. Yes, this is what we have here. So he did apply my mapping. Okay, my documents are coming. But still, when we are searching, we are still searching within the regular fields. And now we want to use the full text field for searching because we have generated that at index time. So let's change that. Here, instead of searching in name, gender, address.city, address.country, I can search here in my full text field. And I can do even something more interesting. I can say, if you find what you are looking for into the name field, then this document will be more relevant than what you have found in the other field. So I want to boost the result and the relevancy, right? So by a factor 3 here. So let's compile that. Okay. Now if I'm searching for Joe, wow, it's working. Okay. If I'm searching inside for France, okay, it's working as well. So we have the same behavior as we have seen before. I still need to do that here for the advanced search. So instead, for the advanced search of searching into name, I can search in my autocomplete field, which is generated at index time. Same here, same here. Okay, so if I'm searching for Joe now, okay, I have the same behavior as before. Do I have people in France? Yes, and in not. Okay, so we are back. Sometime I have this question about as you are indexing into Elasticsearch within the same transaction as you are sending your document to the database, do you have a risk to slow down the injection rate for your database? So I want to demonstrate that Elasticsearch is not the pain point here. So in my person service, what I'm going to do, I'm simply going to remove all the call to the database, and I'm just going to save my document into Elasticsearch. Okay. So if you remember, when I'm injecting 10,000 documents, I'm able to inject about at that rate. So let's inject again, 10,000 documents. Done. Okay, so it was much faster. So as it's super fast, I can inject 1 million documents now. Let's do it. So I'm injecting 1 million documents, and Elasticsearch is a near real-time search engine. So while you are indexing document, you can start to search, right? And it's efficient. You can see the number of documents coming up and up and up. Okay? This is why a search engine is built for, to be efficient. Okay. Let's do something more interesting now. We can do some computation on top of the data we are injecting. And for example, I want to compute some aggregations. I'm adding here, after my query, some aggregations. So what I'm doing here, I want to compute an aggregation. I want to compute the total number of documents broken by country. Okay, and I want to get back the 10 first top countries I have in my data set. I want also to compute another aggregation. I want to have the distribution of my documents broken by year. So I'm building here a date histogram. On the date of birth field, I want an interval per year. And this is basically what this is doing. So let's run it again. Okay, if I search again, I can see now the distribution of my, oh, by the way, my 1 million documents is done, okay? If I look at the rate now, I was able to inject, whoa, that's a lot. I was not expecting so many documents per second. to be honest. That's cool. Oh, no, sorry. That's not the good one. Good one is here. Okay, I was expecting that number. 12,000 documents per second on my laptop. So, when I run my query now, I can see the distribution of my documents broken by country and broken by years. So here on the interface, I'm reducing every 10 years, but this is the same thing. And I'm able to search. If I search for my Joe here, okay, I have the distribution of my Joe broken by country and broken by year. And if I want to do a filter on navigation, I can say, I want to click on that button and I want to only filter my documents using living in France, for example. Or I can implement that. So let's do it. It's, again, somehow easy. In the search method, I'm getting from the interface a filter by country and a filter by date fields. So what I can do here is to wrap my query. So if I have anything in the filter by country or filter by date, I want to wrap my query here inside a Boolean query. So the criteria I have here must be respected. And in addition to that, I want to filter my result. And I want to filter using here a term query with the country content. And for the date, I'm going to use a range query between two dates. So the date which is provided by the interface plus 10 years. So I want to filter by date of birth between two dates. So the date plus the date plus 10 years. Sorry. Okay, let's compile that. And now if I'm searching for Joe, I can see only Joe living in France and in the 50s, for example, and for all my data sets. Okay. So I have a faceted navigation feature here, right? Can we do more? Yes, we can. Oops. We can build some more advanced compute capabilities to our project. Here, instead of simply building an aggregation by country, I'm going to replace that by this one. So I'm still doing a first level of aggregation, which is, again, by country. But for each country I am generating, I want to compute the distribution of my data broken by year for around every 10 years. We don't have the support for years here. That's strange, but we don't have it now. So for almost every 10 years. So I will have the repartition of my document per country, then per 10 years. And for every single bucket for those 10 years, I want to compute here the average number of children, right? So I have an aggregation of aggregation of aggregation. So I'm building a tree of aggregation. I need to change something in the interface. This is the only code you will see from the interface. I need to activate this new feature. Okay. And let's reload our application. I have now this compute button. And you can see the result here. So I have my distribution of my documents per country, then per almost 10 years, and then per bucket, the average number of children. If I search for Joe, okay. So it's pretty fast on 1 million documents, right? If I'm searching only for males, okay, I have the males, right? And this is what you can do with Elasticsearch. Okay, I'm almost done. I want to speak about another thing really quickly. What happens if you want at some point to stop Elasticsearch because you have some maintenance operation or your Elasticsearch cluster is not running, which I would not expect, but might happen. So you can, for example, instead of sending directly into Elasticsearch, you can use brokers. Instead of sending to Elasticsearch, you send to a message queue system. Then you write some code, which is subscribing to the message queue, and then sending that to Elasticsearch. Okay? You can use Redis or Kafka or RabbitMQ, for example. Those are great products to do a message queue system. Instead of writing your own code within your application, you can also use Logstash. So Logstash is a tool we are building at Elastic. So it basically helps you to stream your data from a source, transform it, and stream it to Elasticsearch or other places if you want. If you want to scale out Logstash, so that's super easy. You can just create new instances and increase your throughput to Elasticsearch. So that's easy. Come with us. And yeah, we have cookies. So as soon as you have indexed some data into Elasticsearch, you can use the Kibana application instead of only using the console. With Kibana, you can build nice dashboard based on what you have indexed and when you want to build them. So everything is, yeah, we put the data in the hands of the end user, right? So you are free to use it as you want. So this is, for example, a representation of the index what I have indexed today. So typically, a dashboard you can build by yourself. Kibana is under Apache 2 license, so you are free to use it. And yeah, and that's it. And I'm done. I think, yeah, I have 5 minutes left, or I don't know if we have time for a question because we were late at the beginning. Thank you for joining the beach. You invited me here. I have some stickers in the front if you want to take stickers at the end of the session.
We do actually have some time for questions. So just to let everyone know, we're running 20 minutes late. We're running 20 minutes late across the board, so you don't have to leave a session early to get to the next one. So up until lunchtime, 20 minutes late, we will get back on time over lunchtime. So don't feel you have to leave a session to make another one. They're all 20 minutes late. But we do have time for questions because of that, if anyone has any questions. There we go. One microphone is on its way.
Hi, good morning. Why we stopped listening about rivers?
You are mentioning the rivers?
Yeah, because for instance, I'm using massively Elasticsearch and MongoDB. And in the beginning, we decided to follow the river approach. Nowadays, everybody advises not to do it, and we somehow are obligated to deal with all the crude manually inside our app, so we need to do some refactoring to indexing our documents. Why is that, basically?
So the reason, so we had this feature called rivers at the beginning, at the early edges of Elasticsearch. Rivers were like an ETL running inside Elasticsearch nodes. And we didn't find really smart to have something which is collecting data from a source, which can be really CPU intensive and maybe put your cluster at risk within an Elasticsearch cluster. And this is the reason we asked the Logstash team to join the board, because we want to have an option to stream data outside Elasticsearch cluster. So my advice would be use Logstash for this, but sadly, I don't think we have a MongoDB input for Logstash. I don't think it's available. Maybe the community build it, but I'm really unsure it exists actually. So yeah, so we deprecated it. We announced it ages ago, maybe 2 years ago, we announced it, please don't use it, because we knew that we are going to remove it, and now it's done. In 2.0, you don't have rivers anymore, so you really need to do something else. Again, my favorite approach is to inject in a while method into the database and Elasticsearch at the same time. So if you have access to your application, that my advice would be, okay, send it to MongoDB for storage purpose, and within the same transaction, send it to Elasticsearch within the same transaction. Otherwise, you need to build yourself a tool probably, or look if the community has built something around this. I know that we have a lot of questions about this because of the MongoDB river, which was popular, but yeah, I'm sorry about that.
Thank you.
Did you understand me? Yeah? Okay, cool. Okay, we are done. Thank you all. Have a nice